we define the equilibrium constant as the representation of the equilibrium position for a particular reaction, and what will be the concentrations of the different reagents and products in that for that reaction in that equilibrium position. And if you have a reaction with reagent A plus B to give you products C and D, and each of them with their particular stoichiometric coefficients, you can define the equilibrium constant for that reaction as the concentration of the reagents, the concentration of the products, sorry, to the power of their coefficients, divided by the product of the concentration of the reagents to the power of their coefficients. So the concentration of products, the product of the concentration of products to the power of their coefficients, divided by the product of the concentration of reagents, each of reagent to the power of its coefficient. And the equilibrium constant is represents the relation between the forward rate constant and the reverse rate constant. So it would be the rate constant of the reaction going forward divided by the rate constant of the reaction going backwards, and together they put together, they represent the equilibrium constant for that reaction. Kc, you can define several equilibrium constants, and you will look into that. Perhaps you already know this, but you will definitely look more into this when you're doing physical chemistry and thermodynamics. One of the ones you can define is Kc, which is related to the concentrations, the one I've mentioned here. And Kc, the equilibrium constant, remains constant for a particular reaction at a given temperature, irrespective of the concentrations of the equilibrium. So it doesn't matter the equilibrium concentrations, but when put together at a particular temperature for that particular reaction, that will give you a equilibrium constant. So it's independent on the concentrations, it's only dependent on the temperature and the type of reaction you are, and the type of reaction that constant applies to. So now I'm going to ask you to stop the video and write an expression for Kc, for the equilibrium constant, for this particular reaction of carbon monoxide and hydrogen. Stop the video now, please. I hope you stopped the video and had a go at the exercise. How would I write the equilibrium constant for this reaction? Well, Kc, the equilibrium constant, would be the product of the concentrations of the products, which are CH4 and water, and they both have a coefficient of 1, because their stoichiometric coefficient is 1 for both of them. And in the denominator I would have the product of the concentration of the reagents, and I have two reagents, carbon monoxide gas, again to the power of 1, and the concentration of hydrogen would be to the power of 3, because that's the stoichiometric coefficient for the hydrogen. What do we use the equilibrium constant for? Well, it can give us, you can interpret it in a qualitative way by looking at the value of the equilibrium constant. The larger the equilibrium constant, the larger the numerator is, the larger the concentration of the products are. That means that a reaction with a large equilibrium constant, the products are favored. You can also use the equilibrium constant to predict the direction of a reaction by calculating called the reaction quotient. And reaction quotient it has the same expression as the equilibrium constant, but the concentrations that you use are at a particular moment in time, so not necessarily in the equilibrium. So you can compare that quotient with the equilibrium constant at that temperature to predict whether the reaction will go forward or reverse for those particular concentrations. And finally, you can use the equilibrium constant to calculate the concentrations of the different reagents and products in the equilibrium. I'm going to ask you to stop the video for a moment and have a go at this exercise. For this particular reaction, the reaction of carbon monoxide with hydrogen to produce methane and water, determine the equilibrium constant when the concentrations in the equilibrium for all those products and reagents are these ones. So stop the video now, please. So I hope you stopped the video and had a go at the exercise. How would I go about solving this? Well, first of all, I need to write the expression of the equilibrium constant, which we have written already in a previous slide, but I will repeat it again. So we have the concentration of methane times the concentration of water, which are the two products, divided by the concentration of the products, of the reagents, sorry, which are CO2 and hydrogen, and that to the power of 3 because of the coefficient. Now, I've got moles, not molarity. Moles are not a unit of concentration, they're a unit of mass, but I can imagine that the volume is 1 liter. To convert all my moles to moles per liter to molarity, and so I can use the moles directly. So I would have the concentration of methane, which would be 0.387 divided by 1. The concentration of water, which is again 0.387. The concentration of carbon monoxide, which is 0.613. And the concentration of hydrogen, which is 1.839 to the power of 3. So by doing the calculations for that mathematical operation, I would have the equilibrium constant for that particular reaction and in that particular at that particular temperature, which gives me those equilibrium concentrations. For gas mixtures, the equilibrium constant can be written instead of concentrations in terms of partial pressures. And then we have something called Kp, in which you look at the partial pressures of the gases. And it's beyond the scope of this module, but you will explore this in quite a lot of detail in Introduction to Physical Chemistry and Thermodynamics. It can be demonstrated that the Kp for a reaction is the Kc, the equilibrium constant, times RT, R being the ideal gas constant, T the temperature in kelvins, to the power of delta N. And delta N is the sum of all the coefficients of the products that are gases minus the sum of all the coefficients of the reagents that are gases. So there's only gas, the gas products, the coefficients minus the coefficients of the reagents that are gases.